So a block is going to get pushed up this ramp. The applied force is given and it's parallel to the ramp where the angle is given. The mass of the block is given. The displacement of 10 meters along the ramp is given, as well as the height of 5 meters. And this works out because it's a 30-degree angle. The height is going to be exactly half of the hypotenuse because sine of 30 equals a half. It also says the block is going at a constant velocity of 4 meters per second, which is important so that we can calculate kinetic energies, and also because we know that the forces have to be balanced. So the problem asks us to get the initial energies of the box, the work done on the box by all the forces acting on it, and then the final energies. And then hopefully we can make some realization at the end and answer question D, which was, what's the point of all this? So this might get a little bit messy. They do ask us to calculate a whole lot of things. So one thing I need to do is state my reference height. And whatever reference height I state, I have to maintain that for the entire problem. So I'm just going to go ahead and let where the box is starting to be the reference height. And that's going to make my first column relatively simple, the initial energies. So my initial kinetic energy is half mv squared. So it's a direct substitution of these values, 2 kilograms, and the speed is 4 squared. So that's going to be 16 joules. And the gravitational potential energy, which is mgh, is going to be 0 joules because I have set my reference height where the block begins. So it's at a height of 0. So it's going to be 0. And then my total mechanical energy would be the sum of these two. So it would be 16 plus 0, which is just 16 joules. Okay, so that's not so bad. That's part A. The works is where it gets a little bit more tricky. So there's 4 forces acting on this box. Actually, I may draw a free body diagram. I got some room at the bottom left here. I have a little bit of room. Okay, so I mean, we're practicing ramp questions again. This is going to be a force of gravity. It's going to be down. And I'm going to break that up into components. Parallel to the ramp and perpendicular to the ramp. So I'll call this FGY, that's perpendicular to the ramp, and FGX, the component that's parallel to the ramp. Apologize, it's kind of small to see. It's got an applied force. Well, yeah, it's got an applied force pointing up the ramp. And I'm going to make a bit longer than FGX because there's also going to be friction resisting it. And I need the forces to balance, so the applied force is going to be the same size as the sum of the friction and FGX. And finally, my normal force needs to balance out the FGY component. Okay, so that free body diagram is going to turn out to be useful when I figure out all of these works. So let's see, what order do they ask us for? The first one, the work done by the applied force. Okay, I'm going to label that as, I'll label that as W sub A, the work done by the applied force. So that's going to be the magnitude of the applied force times the displacement times cosine of the angle between the applied force and the displacement. So I'm actually going to fill in the number for the angle right here. And the applied force and the displacement are in the exact same direction. They're both aimed up the ramp and parallel to the ramp. So in that case, the angle we use is 0 degrees. There's no angular difference between the applied force and the displacement. Cosine 0 is equal to 1. So, and when you multiply anything by 1, it doesn't change the value. So it basically cancels out. I'll put a 1 there. Okay, I'll keep on going. So the applied force is 13.8 newtons. The displacement is 10.0 meters. So that gives a total of positive 138 joules. So that's the work done by the applied force. Secondly, I'll go with, what did they ask for next? Friction. Okay. And C is gravity. So friction's going to be a bit trickier. Going back to the free body diagram, I'm going to fill in some values. So my applied force is 13.8 newtons. How many newtons is my friction? Well, to do that, I actually first need to calculate my FGX, see how many newtons is pointing down the ramp due to gravity. And that's going to be mg sine of 30 degrees. Given a mass of 2 and a g value of 9.8, and sine of 30 is equal to a half, actually. So that's pretty nice because you have 2 times a half, which is 1, times 9.8, giving us 9.8 newtons. So the gravity in the x component is 9.8 newtons. And that actually means that friction, that means I can figure out the value for that. Because it's constant velocity, forces have to balance. Friction is going to have to end up being the difference between 13.8 and 9.8, which would be 4 newtons. Okay, so now I'm ready to calculate the work done by friction. I'll denote that with W subscript F. So that'll be the force of friction times the displacement times the cosine of the angle between the friction and the displacement. So the friction points down the ramp, while displacement points up the ramp. They are parallel, however, pointing in directly opposite directions. So if you have 2 arrows pointing in the opposite direction, they're actually 180 degrees apart in terms of angular separation. So cos 180 goes in there. Now cosine of 180 is equal to negative 1. So I'll just put a negative in front of all this. And the force of friction I calculated in my free body diagram to be 4. And the displacement is 10. Giving us a value of negative 40 joules overall. So friction does negative work on this box. Now I'll turn my attention to gravity. Work done by gravity. So that'll be the force of gravity times the displacement times cosine of the angle between gravity and the displacement. This one's a little trickier. I'm going to go to the system diagram drawn at the top there. So the displacement is pointing up the ramp. I'll put a yellow arrow there. That's the direction of the displacement. Whereas the force of gravity points straight down. So I'll draw a down arrow there. So the angle theta we use in this formula is this angle that's in between these 2 yellow arrows I just drew. That angle is more than 90 degrees. How much more? Well, it looks like it's 30 degrees more at the angle of the ramp. So the angle that goes there is actually 120 degrees. 120 degrees. Um, it's an obtuse angle, so the answer is going to end up being negative. And if you look at the yellow arrows I drew, they're slightly opposing each other. They're not directly opposing each other, but they are kind of opposing each other. And that's going to make the work value turn out to be negative. Okay, the force of gravity is mg. And cosine of 120, that's actually a special angle, and that's going to equal to negative a half. The mass is 2, g is 9.8, displacement's 10, and then we've got this negative a half. So that's not so bad, because 2 times negative a half makes negative 1, and then 9.8 times 10 makes 98. So this is actually just going to be negative 98. Okay, so that's the work done by gravity. And finally, the work done by the normal force. The work done by the normal force is going to be the force of normal times the displacement. And now let's consider the angle here. What's the angle between the normal force and the displacement? I'm going to use the same diagram that I just kind of used. I'm going to draw the normal force now in green. There's a normal force, and that's actually making a 90-degree angle with the displacement. So the angle I'm going to throw in there is 90 degrees. They are perpendicular, and cosine of 90 degrees equals to 0. So the normal force does no work on this box. So now I've calculated all the individual works. I can actually find the net work, the total work. So when I add these up, 138, negative 40, negative 98, and 0, that actually turns out to be a nice solid 0 joules. So the net work done on the object is actually 0 joules. So now realizing that I actually did not really want this to happen, and I'm realizing my mistake. But that's a story for another day. Okay, so it did happen, so we're going to go from here and just finish the last part of the question. We'll calculate the final energies. So the kinetic energy, half mv squared. This is going at a constant velocity, so that the kinetic energy actually never changed because it remained at 4 meters per second the whole entire time. So it's going to be the same answer as part A. The gravitational potential energy the gravitational potential energy, mgh, that's going to be different. So I have a height now of 5 meters. So the mass is 2, the g is 9.8, the height is 5 meters. So 2 times 5 is 10, 10 times 9.8 is 98 joules. Okay, so now my new total mechanical energy is 16 plus 98. That'll be 114 joules. Okay. So the energy of the box increased. It went from 16 joules to 114 joules. So you may have learned a little bit from grade 11 about energy, and you may think, oh, well, there's got to be something wrong, because isn't energy supposed to be conserved? Why did the number change? And you would have thought that was true also because maybe you just solved problem 4 and saw that the energy never changed. So why did the energy change in this situation? Mechanical energy can change. Okay, mechanical energy can change, and it will change if you have forces that are called non-conservative forces that act on the object. Forces called non-conservative forces that act on the object. And what's a conservative force and what's a non-conservative force? A conservative force is, we'll get into that another day, but in this case, out of all of the forces we calculated the work for, only gravity is a conservative force. The other 3 were non-conservative, though the normal force doesn't really matter because it was 0 anyway. But applied and friction, we call these non-conservative. So the mechanical energy, I guess one point, it was kind of by accident, I didn't mean this, but one point is that the starting mechanical energy will increase or decrease depending on how many joules of work were done on it by non-conservative forces. I symbolize that with W subscript NC, the work done by non-conservative forces. And then we end up with the ending number of joules. So both energy and work are measured in joules. So what I'm saying is we start with a number of joules. In this case, we start with 16 joules. And due to the work done by the non-conservative forces of applied and friction force, we actually end up adding 98 joules to it. If you do 138 minus 40, which are the 2 values there, that makes 98. And you actually see 98, you see 98 right there on the right side as well. So we started with 16 joules of energy. We added 98 joules to it through doing work on it. And that's how we end up with 114 joules overall. So that's kind of where this first half of the unit is heading. This unit's called energy and momentum. So yeah, this last concept here, that's going to be the main focus of the energy half of this unit.